Assalamualaikum warahmatullahi wabarakatuh, and a very good evening. I bid to the head of School of Chemistry and Faculty of Applied Sciences UiTM Negeri Sembilan, Prof. Madya Technologist CHM Dr. Sheikh Ahmad Izzadin bin Sheikh Muhammad Ghazali, our guest speaker Dr. Gani Purwiandono, and fellow participants. I am Siti Nazrina binti Yahya, and I will be your moderator for today. It is a great pleasure for me to introduce our guest speaker today, who is going to share with us about bonding in material chemistry. Our guest speaker graduated with a bachelor's and master's in Department of Chemistry at Universitas Gadjah Mada, Indonesia, and PhD in Engineering at Gifu University of Japan. He is currently working as a lecturer of Faculty Mathematics and Natural Sciences in Universitas Islam Indonesia. He has also published 9 publications throughout the past 5 years. So before we start, I would like to invite everyone to turn on their camera for a photo session. So, 1, 2, 3. 1, 2, 3. Okay, thank you. Without further ado, please welcome Dr. Gani Purwiandono to deliver his presentation.
Okay, thank you very much. Ya, Assalamualaikum warahmatullahi wabarakatuh. Bismillah, alhamdulillah, salatu wassalamu ala rasulillah, amma ba'd. To the Honorable Professor Dr. Izzadin, to the Honorable Lecturer from UiTM, Department of Applied Chemistry, and also to the student, and also to our moderator, Ms. Siti Nur Zurina Yahya. Thank you very much. I would like to thanks for your opportunity that you give me to stand here and present one of the chemistry issues about chemical material chemistry or chemical bonding. So let me share my screen. Which one? This one. I want to share. Okay. Can you see my screen?
Yes.
Okay, yeah. Okay, yeah, thank you very much. Hide this one. Okay. Is it possible for me to cut the second screen? I mean, the Google Meet screen and also the presentation. Yeah, I never do the presentation using Google Meet before, sorry. maybe this one. Is it okay? Okay. Yeah. If you have any question, please feel free to ask me. Then first of all, I would like to thanks and also for this opportunity. I will do my presentation in maybe in 40 until 50 minutes because 1 hour and 30 is too long for me. So in this session, I would like to share about material chemistry, especially the focuses on the bonding, the chemical bondings. My name is Gani Purwiandono from the Department of Chemistry, Universitas Islam Indonesia. For the outline in this session, the first in the chapter 1, I would like to describe about the basic quantum chemistry of elements, and then we will discuss about the atomic bonding, then the types and properties of the bonding, and the last part is the material infrastructure. So let's start with the chapter 1, the basic quantum chemistry of elements. And here the flow chart, quantum mechanics or quantum chemistry in the first part is the historical background. To understand the formation of chemical bonds, of course, we need to know about the electronic structure of atoms. Because light gives us the information about the structure, we usually begin by discussing the nature of light. Then after that, we look at the Bohr theory of the simplest atom, this one. For the example, hydrogen. The Bohr theory firmly established the concept of energy levels, but fails to account for the details of atomic structure. Then we discuss some basic notion of quantum mechanics, which is the theory currently applied to extremely small particles such as electron in an atom. Then if we want to talk about the wave versus particles, the definition of the particles is continuously repeating change or oscillation in matter or in physical field. Of course, light is an electromagnetic wave consisting of oscillation in electric and magnetic fields. Then move to the Broglie's hypothesis. The first clue in the development of quantum theory came with the discovery of the Broglie relation. In 1923, Louis de Broglie reasoned that if light exhibits particle aspects, perhaps particles of matter show characteristic of waves. Then he postulated that a particle with a mass and velocity has an associated with a wavelength. And we know the famous the equation lambda equal with h, or the Broglie constant per mass and velocity. And then we can use the quantum tools, especially for the Heisenberg and also the postulates to get the detailed information about the quantum mechanics, especially for the quantum chemistry. And from this information, from this basic quantum chemistry, we can get the information about the detail of the geometry, the structure, and the size and also shape of each atoms. Go to the next slide. Yeah, the next clue is the failures of classical physics. The failure of classical physics divided into 3 until 4 experiments. The most important experiments, of course. The first one is the line spectra of atoms. The second one is the black body radiation. Then the heat capacity of solids. And the last one is photoelectric effect. For the line spectra atoms, it means show only certain, we can see in this slide, emission line spectra. Line spectra of atom, it means show only certain colors, specific wavelength of light. Then atoms are heated, they emit lights. This process produces a line spectrum that is specific to that atoms, of course. And the second experiment is the black body radiation. For the black body radiation, we can get the information by increasing the temperature, the energy distribution will increase, and the wavelength will decrease, amid the color change with the shift of the wavelength. So by increasing the temperature, the color of the black body radiation will be changed too. And for the heat capacity of solids, the same explanation with the black body radiation. And the last one for the photoelectric effect. For the photoelectric effect, if the ejection of electrons from the surface of metal when light shines on it, and also electrons are ejected only if the light exceeds a certain, and then they should same with the current frequencies. Then we move to the quantum tools to get the information about how we can solve the failure of the quantum mechanics from 3 until 4 experiments before. The first one by the Heisenberg uncertainty principles is the correlation that states that the product of the uncertainty position denoted by delta x and the uncertainty of momentum denoted by m and delta phi of a particle can be no longer than h per 4 pi. And this is the feature of the diffraction electron by a slit. Heisenberg conducted a thorough experiment as well. He considered trying to measure the position of an electron with gamma ray, and then the illuminates electron changing its momentum in an uncertain way, of course. So by this research, we got the information about the uncertainty theory rules from the Heisenberg uncertainty. And the last part of the quantum tools is the postulates. The square of the wave function, or psi square, is the probability, this density for finding the particle at the current location. And there are several principles for the wave function. Must be single valued, also continuous the first derivatives, and also quadratically integrable. And one of the most important things in the application of material chemistry is the correlation between the wave function and the probability. So for us, maybe for chemistry student, the most important things we should know about the correlation between wave function denoted by the psi square, this one, And the meaning of the wave function, also the probability or a density to finding a particle in the current location. So after we got the information about whole process in quantum chemistry, until we know the Schrodinger equation, we got the information, we got the most important things for the quantum mechanics divided into 4 quantum numbers. Figure A illustrates the probability density for an electron in hydrogen, and figure B shows the probability of finding the electron at various distances from the nucleus. In the figure A, the concentric circles represent successive shells. And then in the figure B, I think the highest probability, most likely, distance is at 50 pm. Then according to the quantum mechanics, each electron is described by 4 quantum numbers, as we know, divided into 4 quantum numbers. The first one is the principal quantum number. The second one, angular momentum quantum number. The third one is magnetic quantum number. And the last one is the spin quantum number. Here the table of the permission values of quantum number for each atomic orbitals. N is the principal quantum number, is the one on which energy of an electron in an atom primarily depends. The smaller of the value of N, the lower the energy, and the smaller of the orbitals, same value of N, are said to be the same shell, this one. And then for the L, angular momentum quantum number, describe the orbitals of a given N shell having different shape. So if the same value of N and L, we can get the information to be in the same shell and subshell. And then for the magnetic quantum number, describes about the orbital of a given N and L of a given energy, and also the shape, but having different orientations. And the last one is the spin quantum number, refers to the two possibility orientation of the spin axis of an electron, either plus half or minus half. So this is the conclusion data after we know the brief information from the quantum chemistry. For the basic quantum chemistry, for the first kind, we know the historical of physical chemistry. We know that the information about the detailed cross-section, shape, energy, and also the orientation. And this one, the cross-sectional and cutways diagrams, view of 1s orbital and also 2s orbitals. And this is the shape of 3 p orbitals, px, py, and pz. Now let's move to the chapter 2. In the chapter 2, we will talk about the atomic bonding, specific for the structure of atoms, and also what kind of bond that can occur between one atom to another atoms. So in this slide, we can get the information about the atom. The first kind data is the diameter, nucleus, electron cloud, proton, and also the neutron. And then the information of the electronic structure of atom, the atomic mass in grams of 6.022. And then the number of atoms or molecules in a mole is called by the Avogadro number. And also chemists measure quantity of atoms and molecules in moles, molar, and also and so on. And atomic number equal with the number of proton, and mass number equal with number of proton plus number of neutron. And electrons vary in the amount of energy they possess, and they occur at certain energy levels or electron shields. Electron shields determine how an atom behaves when it encounters other atoms. I think this information is the most important information for us, for chemists. And then why we should learn about the electrons. Elements also have a different electron configuration, therefore different levels of bonding. Valence electrons determine all of the following properties in materials such as chemical, electrical, thermal, optical, and so on. The first kind of the atomic bonding, we should talk about the interaction of interatomic bonding. If we learn about the quantum chemistry, we can get the information about the Lennard-Jones potential. The Lennard-Jones potential shows the range of each atom versus the energy repulsion. So in the interatomic bonding, a bond results from the attraction of nucleus for electrons, and then all atoms are trying to achieve a stable octet, of course. Or in other words, we can say that the protons in one nucleus are attracted to the electrons of another atom. Then if we learn about the interatomic bonding, we should know about the primary bonds, secondary bonding, secondary bonds, bonding forces, and also the energies and also material properties of bonding. Primary bonds, it means strong bond energy. It's about 100 until 1000 kilojoule per mole, with the electrons are transferred, either transfer or shared. Yeah, transfer or shared to each other. And then secondary bonds, it means no electron transferred or shared with the bond energy less than 100 kilojoule per mole, or less than 1 electron volt per atom. Then we will discuss about the specific interaction between primary, secondary bonding forces and energy, and also material properties of bonding. Let's check for the primary bonding force. The primary bonding is divided into 3 kinds of interaction. First, the ionic. The second one is covalent. And the third one is metallic. Ionic, it means transfer of valence electrons, and covalent means sharing of valence electron with the directional pattern, and the metallic means the localization of valence electron. For the ionic bonding, yeah, maybe we can check it later. And then for the secondary or van der Waals bonding, divided into 3 until 4. First is the dipole-dipole, and then H bond, hydrogen bond, then polar molecule induced dipole, and the last one is fluctuating dipole. That is the weakest from the secondary or van der Waals bonding. Then let's check for the ionic bond, primary bondings. The definition of primary bonding: the electron are transferred, either transfer or shared to each other. The strong bond energy equal with 100 until 1000 kilojoule per mole. And then for the bond length, only 0.1 until 0.2 millimeter. And for the ionic, it means transfer of valence electron. For the example, sodium chloride, which has a strong Coulomb interaction between a positive atom, cation, and negative atom or anion. The molecular base theory, for the two kind of the basic theory, 2 until 3. The first is the valence bond theory, and then molecular orbital theory, and then the crystal field theory. In molecular orbital theory, for the ionic bonding, the orbit diagram for ionic compounds as if they are extremely polar bonds in which electrons are not shifted but are transferred completely to the more electronegative atom. So if we want to know about the detailed ionic bond, we should know about the electronegativity of each atoms. Yeah, and then for the covalent, it means the electrons shared between the atom. For example, hydrogen. For the metallic atoms, some electrons from valence band, those electrons are shared by all the materials. Yeah, the detailed information about ionic bonding is due to electrostatic force of attraction between cations and also the ions. We can see this slide that the electropositive element, for example, sodium, the electron from the electropositive element will transfer to the electronegative element or atom, for example, chloride. So the interaction between cation and anion will occurs the ionic bonds. The electron density is shifted toward the more electronegative atom, since that atom contributes more to the lowest energy bonding molecular orbitals. The definition of bonding here is characterized by the transfer of one electron from cations to anions, and is almost entirely electrostatic, as you know. Then, if we want to know the detail about the ionic bonds, we should know about the formation about the electronegativity for each element. The ionic bonds, it means large difference in electronegativity with the delta electronegativity more than 2. From this table, we can get the information for about the electronegativity data for each atoms. This one and this one. The electronegativity varies in a predictable way across the periodic table, of course. And then the electronegativity increase, this one, the electronegativity, and also this one, the electronegativity increase from bottom to the top in the groups, and increase from left to the right across periods. This one from the bottom to the top and from left to the right. And those fluorine, this one, is the most electronegative element, while francium, francium, this one, is the one of the least electron for the electronegative. Okay. Then we will go to the example for the ionic bonding in sodium chloride. This one. Ionic bonding in sodium chloride forming from the cation, sodium cation, and chlorine ion, forming an ionic bond, of course. The electrons orbital generally do not overlap, this one. Only strong force of attraction, Coulombic force, between positive and negative charge, this one. And then from this feature, we can get the information. One electron from sodium will transfer to the chlorine atoms to make the wall ionic for sodium and chlorine. Okay. This theory will make the basic information for how to the bulk material can made for. Then we will discuss about ion arrangement in ionic solids. For the ionic bonds are non-directional. Geometric arrangements are present in solids to maintain electric neutrality. For the example, sodium chloride, we know the 6, 1, 2, 3, 4, 5, 6, yeah, this one. Will pack around the central of sodium ions. The detail for the ion arrangement in ionic solid, it means ionic crystals are crystals made up of ions, of course, that are held together by electrostatic attraction. Crystal lattice, the description of crystal lattice, maybe you can get from the information from XRD data. Yeah. Crystal lattice is a regular geometric arrangement of ions that has a regular symmetrical arrangement of ions. So as the ratio of cation and anion radius decrease, fewer anion surround central cation. Okay. Then we will go to the properties of ionic solids. Maybe if you have any question. Yeah. I'm sorry. Yeah, we will go to the properties of ionic solids. The properties of ionic solid, it means the structure of ionic solids is determined by how the cation and anion can pick together. Yeah, here is the properties of ionic solids, and here this the description, the brief description of the properties of ionic solid. We will discuss it later, maybe. And the first kind of the property of ionic solid, ionic materials are characteristically hard and brittle. Yeah, this one maybe. Yeah. The reason of these properties, because the because the ions in ionic solid are, yeah, because the ions in ionic solid are held in lattice due to the electrostatic forces of attraction in cations and anions, as well as the repulsion with the like charges. So that's why ionic material are hard and also brittle. And then the second property, it's also thermally insulative, electrically insulative if ion static. May I ask to the student maybe why maybe Nur Ifah? Hello?
Yes, sir.
Okay, yeah. For the second property, the ionic solid, they have the specific property about the thermal. They are thermally insulative. Do you have maybe any suggestion, maybe, what the reason why the ionic solid have such property? Hello? Hello? Pass? Maybe.
Sir,
Okay, yeah.
Can you repeat the question?
Yeah, the second, this one. Can you see the presentation? Hello?
Yes, sir.
Yeah, it just talk about the properties of the ionic solid. The first kind of the property of ionic solid is the characteristically hard and brittle, and the second one is the thermally insulative. So, do you have any suggestion why the ionic solid has the thermally insulative, maybe? Yeah, it means the ionic substances will not conduct electricity as solid. Thermally insulative.
Because the ion has a fixed position and cannot move.
Okay. Yeah. Yeah, that's the correct answer. Thank you. Yeah. The second part for the properties of the ionic solids, ionic compounds, ionic substances will not conduct electricity as solid. This is due to the fact that the ions are not free to move. Yeah, are not free to move in a solid, as they are arranged in an ionic lattice. Then if we want to change that property, we just dissolve it in the molten phase for the allowing the ions to move freely, and so conduction will occur. Yeah, that's the answer. Thank you. And the third property, it exhibits high melting temperature. Yeah, maybe I will ask another student. Shafi, Muhammad Shafi. Muhammad Shafi.
Yes, sir.
Okay, yeah, okay. Yeah. Do you have any suggestion why the ionic solids have the high melting point for the temperature? This is the data for the melting point. Maybe.
Because ionic bond is the strongest bond.
Okay. Yeah. Okay. Okay. Thank you for the answer. So, yeah. For the ionic solid, yeah, ionic solid or ionic compounds are held together by strong electrostatic force of attraction between oppositely charged ions. It means from cation and anion. The large amount of energy needed to break the many strong bonds. So that's why we need high temperature to break the strong electrostatic forces between cation and anion. So that's why the data of the melting point more than 100 degrees C for each compound. Yeah, thank you for the answer. Yeah, I think this is the last one of the properties of ionic solids. The lattice energy and melting point of anically bonded solids are high, of course. And then the lattice energy decreases when size of ion increases. The lattice energy decreases when size of ion increases. Yeah. And for the multiple bonding electrons, increase lattice of energy. For the example, this one maybe for the sodium chloride, the lattice energy 766. And then sodium chloride 635 and so on. Yeah, because the main reason for this data is the large of energy needed to break the many strong bonds between strong electrostatic forces of attraction between cation and anion. Yeah, I think that's all for the ionic bond. And let's move to the covalent bonding. The covalent bonding for the non-metal atoms bond with each other by sharing. The key point of the covalent bond description is the share of electron or the shells of the electrons. The covalent bond is directional. Yeah, in covalent bonding, author S and P electrons are shared between two atoms to obtain Nobel gas configuration or octet rules. Then takes place between elements with small difference in electronegativity and close by in periodic table. Yeah, this is the for water. And here the example for each single, double, and triple bond for each covalent bonding example. The first one is the fluorine gases. The outer orbital is 2s2 and 2p5. Share one of p electron to attain the gas configuration like this one. And then for the oxygen, they should share two electrons from p electrons to get the Nobel gas configuration, make the double bonding for these molecules. And then the last one is the nitrogen. They should share with a 3 electron from p orbitals to get the stable noble gas configuration. Yeah, the bond energy for single bond 160 and double bond 28. I think I made a mistake maybe. Yeah, I will check it later. The triple bond is 54 kilojoule per mole. And then the covalent bonding in carbon. The carbon has electronic configuration 1s2, 2s2, 2p2, and they should make the hybridization because one of the 2s orbitals promote to the 2p orbital, result for sp3 orbitals. This one indicated for covalent bonds are formed. Yeah, this is the example for the covalent bond. The structure of diamond for sp3 orbitals are directed symmetrically toward corners of regular tetrahedron. And the shape of the molecule is tetrahedral, of course. Edge of the regular tetrahedron, this one, and also this one, are separated by an angle of 109 yeah, degree, and so they are become sp3 orbitals. Yeah, the detail for the diamond, they have 3-dimensional structure based on tetrahedrali bonded carbon atoms and all single bonds. They have specific properties such as very hard, very high melting point. It does conduct electricity, and also the crystal structure of diamond is phase center cubic, FCC, with the 4 lattice each, with the lattice of each carbon atom joins 4 other carbon atoms in regular tetrahedrons. And as there are no free electrons available, and all 4 electrons have been used up for bonding. And also diamond is transparent, strong, and very hard. It is a suburb cutting tool. Of course, atoms in diamond are very strongly held in position. We will discuss about the diamond and graphite in the end of this presentation. And then for the graphite, 2-dimensional layer structure based on the carbon atoms bonded in triangular planar arrangement. This one. Yeah, each carbon atom forms 2 single and 1 double bond with its neighbor. And we know the specific properties such as layers held together by dispersion forces, very soft, very high melting point, conducts electricity as a result of the delocalized electron. And also graphite is a big covalent structure network. Yeah, with each carbon atom joined with 3. Yeah, with 3 other carbon atom with covalent bonds. Each carbon atom is sp2. This one is sp2. These carbon atoms form a layer-like arrangement of carbon atoms. And these layers have weak forces between them. This one. This is the secondary bonds, yeah, or the weak forces between layers to another layers. Okay. Yeah. I have an issues about the discussion, the differences between molecular covalent solids and network covalent solids. Covalent solids, for example, water, ice, and network covalent solids, for example, diamond. What is the differences between the covalent solids and network covalent solids? Maybe I will ask the student. Which one? Mariam Nazira. Hello.
Yes.
Okay. Do you have any suggestion for these issues? Do you know
Okay.
the differences between the covalent solids and network covalent solids?
Network covalent is a compound that atoms are bonded by a covalent bond in a continuous work, which it has a high melting point, boiling point, and hardness due to presence of strong covalent bond between atoms. And for molecular covalent, molecule having covalent bond is weak due to intermolecular forces that has low melting point and boiling point.
Okay. Yeah. Okay, thank you for the answer. That's correct. Yeah. I think I should finish my presentation. Yeah. The differences between molecular covalent solids and network covalent solids. Of course, there are two type of solid compounds. Yeah, either molecular covalent solids or network covalent solids. The key difference is that the molecular solids form due to the action of van der Waals forces. Yeah, whereas covalent network solids forms due to the action of covalent chemical bonds. So the molecular solids have low melting point, of course, while covalent network solids have quite high melting points in comparison. And also,
Yes, sir.
okay, yeah, yeah, we still have, yeah, maybe I just need 10 minutes to finish my presentation. No problem. Okay, 28. This one, yeah. Okay, yeah. Of course, the molecular solid and covalent solid are two type of solid compounds. Yeah. Um, and the key difference is that the molecular solids form the networks. So let's have a million and the covalent networks connecting point. And others of something like this one. Okay. Yeah. I think that's how they got to the last part on metals and metallic material have 1, 2, or at most 3 valence electrons. Are these valence electrons more or less free to thrive throughout the entire material, the entire metal, forming a C electron? The detailed information you can get from field theory. Okay. The metallic bonding is the strong electrostatic attraction between glacially packed positive metal ions and a C delocalized electron, sodium, and Al, aluminum, aluminum, cobalt, and so on. This is the schematic illustration of the metallic bonding. This is the color one is the ion cores, and this is the C electrons. For the metallic bond is a type of chemical bond in which a cloud of free moving valence electrons is bonded to the positively charged ion in a metal. It can be described as the sharing of free electrons among lattice, among a lattice positive charge metal ions. And also the structure of metallic bonds is entirely different from that ionic metal is the only substance contains a metallic bond. The electrons are moved freely. However, the interaction between ions and electrons are still prevalent. This interaction gives rise to a binding force that holds the metallic crystal together. So this is the this force is the crystal field theory. From the crystal field theory. And then the properties of metallic bonding. The metallic materials have moderate melting point, and also metallic materials are soft and deformable. And also metallic material are excellent electrical conductor due to the localized nature of electron, because the concept of C of electron. Metals are also thermal conductor due to thermal atomic vibration across the metallic body. The basic concept of the metallic bonding is this one, C of electrons. With this theory, you got the whole information about the properties of metallic bonding, such as the melting point, and then soft, formable, delocalized, and also the thermal, and also thermal and electricity conductor, and so on. That's all for the primary bonding. And then we go to the secondary bonding. Secondary bonding due to attraction of electric poles in atom and molecules. Poles are created when positive and negative charge centers exist. This is the equation. the dipole, as long as they can got the good directional for the symmetrical distribution of electronic charge. So we can made the fluctuative dipoles, such as weak secondary bonds in noble gases. Dipoles are created due to the asymmetrical distribution of electron charges and also cloud electron charge. The key point of the dipole is the electron. Sometimes the dipoles with the permanent interaction between each other, and then the hydrogen bond, the most typical bond is the water. The interaction between this one, hydrogen and oxygen from water, from the atom of water. Dipole is created due to the asymmetrical arrangement of hydrogen atoms, attraction between positive oxygen pole and negative hydrogen poles. This is the summary for the ionic, covalent, metallic. The bond energy large. For the ionic, variable, and metallic also the variable. Non-directional, directional, non-directional, and the secondary smalls, directional, interchain poly, such as the polymer, and also intermolecular. This is the data of the summarize of the atom molecular, ionic, metallic, and also the covalent network. You can get this information for the detail. Yeah, I think that's all for the detailed information for the chemical bonding in primary and secondary bonding for each element. And then go to the chapter 3, types and properties of the bonding. Material with large bonding energy usually have high melting temperatures because the large amount of energy. Material with large bonding energies usually have high melting temperatures because the large amount of energy needed to break the many strong bonds. The relation between the magnitude of the bonding energy and the state of the material solids have large bonding energy. Solids are generally held together by ionic or strong covalent bonding, as you know, and the attractive force is between the atom, ions, or molecules in solids are very strong. That's why solids have large bonding energies. And then liquids tend to have relatively energies, because the particles of solids are relatively close together, but not as close as the solid. The particle in a liquid have a more kinetic energy than the particles in a solid phase. I will repeat it again. The particle in liquid have more kinetic energy than the particle in a solid phase. That's why liquids tend to have relatively energies compared with the solid phase. And then the expansion or contraction during heating, cooling, or cooling material is related to the shape. As we know that the material expand or contract when subjected to change in temperature. Sometimes or most likely material expand when they are heated and contract when they are cooled. And then when free to deform, constrict will expand or contract due to fluctuative condition in the temperature. So that's why the expansion or contraction during heating or cooling of material is related to the shape of its material. And then deep neural which typically occurs for material having large bonding energy usually imply a low coefficient of thermal expansion. Okay. Okay. As bond strength increases, as bond strength increases, the atom in the bond are pulled more tightly together. I will repeat it again. As bond strength increases, the atoms in the bond are pulled more tightly together. Therefore, generally or most likely, as the bond energy increases, the bond length will be decreases. Yeah. As the bond energy increases, the bond length will be decreases. Yeah, so that's why for the material have large bonding energy imply the low coefficient of the thermal expansion. Yeah. Do you understand? Maybe. Do you have any question? No question? Okay, we'll continue again. And then for the bond energies type type of materials such as in ceramics, ionic and covalent bonding, large bond energy, large melting temperature, large elastic modulus Young, and small thermal expansion. And then the metal moderate melting temperature, moderate elastic modulus, and then moderate of the thermal expansion. And polymer also small, large thermal expansion, because the secondary bonding, this is the key point for the polymers. Why they have the large of the thermal expansion. Okay, this is the detail. Fine ceramics will not expand more clearly than the metals. This is the properties of the bonding. For example, for bond length, bond energy, melting temperature. If you understand for this data and the reasonability data, we can got the good explanation for the properties from the bonding for each properties, such as the melting temperature, modulus elasticity, and so on. Okay, the last one is the chapter 4, material infrastructure. I just insert for the two kind of infrastructure material for diamond and graphite, and also for the carbon. As you know, for the diamond, every atom is bonded to 4 other atoms, and also it doesn't conduct electricity. For the graphite, has layers formed from hexagonal rings. This one, hexagonal rings. Every carbon atom strongly to other carbon atoms by 3 covalent bonds. And the interaction between the layers is the weak interaction, such as the van der Waals or secondary interaction, secondary bond interaction between its layers. And then the future other form of carbon, such as fullerene, C60, the carbon are bonded covalently into a football shape. Yeah, this one. And also the carbon nanotube. The carbon nanotube is like rolled graphite. It conducts electricity. It's very small. 10,000 times thinner than a human hair. Crystals can be grown inside the pore of the carbon nanotube. They may solve the problem of how to produce small circuits where they might replace wires. This is the human hair, and this is the carbon nanotube. Yeah, I think it's all. Thank you very much. I've added the references and I have several questions for you for the discussion. If we have more time, maybe next time, maybe. Yeah, and then this is the I just copy from the previous presentation. Okay. Yeah, I think that's all. Thank you very much for your attention, for your answer. Okay, we're back to the moderator, Ibu Surina. Thank you.
Thank you so much, Dr. Gani, for the interesting lecture. Now, if anyone have any question, I'm sure Dr. Gani will be pleased to answer them. So I will now open for question and answer session.
I think not for the question and answer, but the discussion session maybe. Okay. Yeah, I think this is the. So this is the. Oh yeah.
Okay,
Okay.
sir. I have one question regarding the chemical bonding. We have you have shared that there are primary and secondary bonding.
Mhm.
So, if I were to ask, what is the difference between chemical bonding and the physical bonding that we use? For example, when welding metals and metals, what is the difference between that type of bonding and the chemical bonding?
Okay. Okay. Chemical and physical bonding. The differences between chemical bonding and physical bonding, right? Hello.
Yes, yes.
Okay. Yeah, the differences between chemical bonding and physical bonding. So, the term of chemical bonding and physical bonding, sometimes in several textbook, they describe the chemical bonding is the primary bonding, such as ionic bonds, covalent bonds. But for the physical bonding, sometimes they describe it about the secondary bonds, such as van der Waals, and then hydrogen bond. Because if we check from, maybe I will show out textbook. Wait a minute. Wait. Okay, yeah, for the example, if we check the book of quantum chemistry, this one, Ira and Nifin, 2006, Prentice Hall. In this textbook, they describe the differences between the chemical and physical bonding depends on the kind of the energy. Yeah, something like if we describe for the primary bonding, the description of primary bonding has the range of energy, the bond energy, about 100 until 1000 kilojoule per mole. But for the secondary bond, less than 100 kilojoule per mole. But in different textbooks, such as the physical chemistry textbook, they describe the physical and chemical bond, not in primary and secondary bond. Yeah, I think that's only the different term between us, chemistry, the basic chemistry for the chemists, and the physics. And then, yeah, that's the answer. And then a different textbook, such as Hagen Lee. Uh, the title of the textbook is term, I forgot the advanced or thermodynamically physical chemistry, I think. Yeah. He said that the chemical bond is the not only from the description of chemical bond, not only from the is it, the description of the energy, but also the kind of microstructure. For the example, if you talk about the interaction between two chemicals with the specific chemicals interaction such as ionic, and also even in the bond, if even in a hydrogen bond, they will say that is the chemical interaction. But if the interaction only occur in the surface of the material, yeah, Huygens said that that is the physical interaction. And also, we can get the information maybe from the journal, the international journals, some the for the specific data from absorption data, interaction data for the kinetic. From the kinetic interaction data, sometimes the author said the interaction between two chemicals, either that is the hydrogen bond, they will say that is the chemical interaction. But if the interaction only occur in the surface, or they occur in the surface, or that's not the permanent interaction, yeah. If we talk about the permanent interaction, we will discuss about the kinetically or time-dependent reaction. So if the interaction, not the permanent interaction occurs, the author, or we will say that the physical interaction. Yeah, at least we have 2 until 3. Yeah, 2 until 3 answer. The first answer is the only the different sum. And the second answer is if we talk about the material chemistry, the interaction between adsorption, inner bulk material, or occur in the surface of material, we can divide it into chemical and physical interaction. But for me, I think I will choose the first one. Yeah, because we are a chemist. We know the detailed information about the bond energy. We know the detailed information about the chemical interaction, and it's clear for us for the interaction ionic bond compared with the hydrogen bond, the interaction between covalent bond compared with the dipole bond, and so on. So that's why the term of the physical and chemical bonds refer to the primary and secondary bonds. I think that's the answer. Yeah, I think that's all. Thank you. Thank you for the question.
Is there any more question from anyone else?
No more question, I think. So this is the student first grade.
Undergrad.
Okay, undergraduate. Okay.
So I have, Doctor, I have one question.
Okay, yeah, please.
In your slide in properties of ionic solid, you mentioned that the lattice energy decreases decrease when the size of ion increase. So what does it
Which
mean
one?
actually?
I forgot the slide. Ionic liquid. This one. No. Which one? I forgot the slide. Okay. This one maybe. This one, right? Right? No? Can you repeat again your question?
Why
Hmm?
the lattice energy
Okay, latest
decrease?
energy. Okay. I'll try to answer your question. I hope I can. Okay, yeah. Okay. Okay. Yeah, as bond strength increase, the atom in the bond are pulled more tightly together. And you get the point? If the bond strength, bond energy increases, the atom in the bond are pulled more tightly together. So that's why generally, if the bond energy increases, the bond length will decreases, right? Okay, yeah, I hope I answered your question. Is it clear?
Yes.
Okay, yeah, thank you for your question. A little bit nervous. Okay,
I have questions, sir.
okay, yeah, please.
So in your previous slide under metallic bonding,
Mhm.
it said that metallic bonding is non-directional. Can you further expand on what does it mean by being non-directional?
Okay, yeah. Uh, Maybe other student can help me. Non-directional. Okay. Yeah, I just want to. mm, which one? The covalent bond. No, this one. Sorry, which one? This one. Okay. The covalent bonding, non-metal atoms bond with each other by sharing outer shell electrons. The covalent bond is directional. Yeah, it means to make the interaction between each atom, either for the s or p orbitals, atom should make the effective range. I will use this data, maybe Leonard Jones potential. This one. Okay. This is okay. Yeah. This is the distance between atom and potential energy. Okay, and this is the distance between the atom. If we want to get the detailed why the covalent bonds occur, we should try to know about the differentiation of the distance for each atoms. I mean, if the distance become higher, there are no interaction between each other. But if the distance becomes more high, the repulsion will occur. So that's why the potential energy will increase. The ideal condition in this part. So in this part, the potential energy will become negative, or we can got the we can relate it to the Gibbs free energy. The Gibbs free energy becomes negative. It means the reaction occurs in spontaneous, and also not only the distance but also the geometrically occurs. It means if, yeah, I will back slide. So if we have the two or more atoms, the interaction will occur only if the range or the direction of each atom becomes ideal. This one. If the range increase, it means no interaction between hydrogen atom and oxygen atom. If the range of hydrogen and oxygen atom become low, it means move to the zero. The repulsion interaction will occur, not the interaction, but the repulsion will occur. But for the metal, I will back to the metal. Which one? This one. Okay, but for the metal, yeah, the basic concept of the C electrons, the basic concept of metallic bond is a type of chemical bond in which a cloud of free moving valence electron. The differences between the covalent bond, the electron cannot move freely, but in the metallic bond, the cloud of the free, the cloud of the cloud of free moving valence electron, the cloud electron can make the electron move freely. So it can be described as the sharing of free electrons among a lattice positively charged metal ions. The structure of metallic bonds is entirely different from that of ionic and covalent bonds. So in a metallic bonds, the electrons are moved freely. However, the interaction between ions and electrons are still prevalent. So that's why the metallic bonding is non-directional. It means not depending on the x-axis, y-axis, or z-axis. As long as they can move freely, the interaction between electron from one metallic atoms and other metallic atoms will occur. That's very different between ionic and covalent bond. In covalent bond, we should use this data, Lennard-Jones potential, the potential of each atom versus the distance of the atom. But for the metallic bond, there are no distance between atoms, between metal atoms, because the concept of this interaction is C electrons or cloud electrons or electron clouds. Yeah, so this for cis is the basis of the metallic bonds. Do you understand? I hope I answered your question. Can you,
Yes, sir. Thank you so
okay,
much.
yeah, thank you for your question. I try to make this simple answer, but I think, yeah,
Is there anyone wanted to ask a question?
yeah, very interesting. Yeah, I think, yeah, thank you for your question. Maybe, maybe it's
Okay, Doctor. If there is no question, no more question, I would like to thank Dr. Gani for the valuable information that you have shared with us today.
okay.
We are very sorry for the inconvenience that we have caused you.
Okay, okay, it's okay, it's okay. And I have shared this presentation, right? Yeah, yeah. Please share to the student. Maybe. Okay.
Before I end this session, for the participant, please don't forget to fill in the attendance in the chat box later. Thank you. Thank you, Doctor.
Thank you. Yeah, thank you. Thank you very much. Time. Okay, see you. See you.
Thank you.
Next.
Thank you, Doctor.
Thank you, Doctor.